So thank you. I'm the Mitsuhiro Sato, the Riken Center for the Computational Science. So in this session, we have the two regular talks and one lightning talks. And for the speaker of the regular talk, we'll have the 20 minutes for the presentation and 5 minutes for the Q&A. So of course, you can post your question on the chat window and the Slack, but you can ask the question directly. In that case, unmute yourself and speak up. Okay, so first speaker is the Mathieu Lobet from the Maison de la Simulation, the CA Skylake. So he received a PhD in 2015 at the CA and Bordeaux University in France on a numerical study of the extremely intensity laser matter interaction. And recently, he in 2017, he joined to the Maison de la Simulation as a CA research engineer. Since then, he participated in various HPC research projects, including the Energy-Oriented Center of the Excellence European project. So today, today's his talk title is Feedback and Result Plotting the particle cell code Smilei on a Fujitsu A64FX processor. Lobet, could you start?
Yes. Thank you very much, Sato, for the presentation and for introducing the title of my talk. So, as you can see, I will talk about particle cell methods and how we managed to get some more interesting performance results on the Fujitsu A64FX processor. So first of all, I would like to spend a small time to present the code. So I mainly worked into the Smilei code. This is an open source and collaborative PIC code, PIC for particle cell. It's massively parallel, mostly designed for CPU systems. We use MPI plus OpenMP. And more recently, we have started to port the code on GPU. We also have a very advanced documentations, a strong visualization tool, and some tools dedicated to make our community more performing, more exchanging. So we have, for instance, an element chat room and many workshops to learn how to use the code. About the modules and the physics, so this code is mainly dedicated to different topics such as laser-matter interactions, but also laboratory astrophysics, particle acceleration. We also have some advanced physical modules such as collisions, ionizations, radiations, and QED. And as I said, we are now focusing on different implementations, different improvements. One of them is the ARM optimization, what I will talk about today, but we're also working on GPU aspects and task-based parallelism. Just before starting the main results, I would like to say that they are preliminary. It is a preliminary work. So it does not reflect the final performance of the code. And as a consequence, any remark, advice, help is very welcome to improve the work and the results. First, I would like to say a few words about the vectorization of the code in the initial state before targeting the ARM-based systems. So quick presentation about the PIC iteration. So the PIC iteration is quite simple, and we can divide one iteration into 4 steps. This is what is presented here, where basically we have the interaction between macroparticles and a structured grid or different structured grids. The first step is called the field interpolation, where we will compute using an interpolation system the fields, I mean the electric and magnetic fields from the grids at the particle positions, and this for all the particles in my system. Then we have the particle pusher, where thanks to the electric and magnetic fields, we can push the particles and move them in the space thanks to the momentum equations. In the third step, we have the opposite of the first one. Here, each particle will generate a current, an electric current. And we write on the node of the current grids the contribution of each particle. And thanks to the electric current, we can compute the Maxwell equations and compute the electric and magnetic fields at the next time step, and then start a new loop, a new loop iteration. About the performance and the bottlenecks, the main bottlenecks are located in the first and third steps. I also forgot to mention that here I'm mostly focusing on the computing steps, but of course, between all of them, we can have synchronizations, we can have communications, we can have I/Os, we can have many different things. But here I'm really focusing on computational things. So as I said, the first one is one bottleneck, particularly for vectorization. It can be vectorized, but if we look at the classical way to implement this particular step, it's not efficient. The second one is quite nice because it can be vectorized easily. The third one is a strong bottleneck because in the classical form, the vectorization is totally impossible due to memory rates. So what we did a few years ago, 3 years ago, was to rewrite these steps to make them more efficient from a vectorization point of view. This work has been mainly done for AVX512 processors and also for AVX2. But we have started to study them also on the ARM-based processor. Also, what we have done is not just implementing a vectorized version, but we kept the two, the scalar one and the vectorized one, in order to be more adaptive. This is what I will talk about here. When we look at the performance of a PIC code, we cannot just look at one specific parameter. We have to consider what we call the number of macroparticles per cell. This is what you can see here on this axis. Because in fact, the performance of a single algorithm will depend strongly on this variable. Here you have the socket time per macroparticle per iteration. What we call socket time is just the runtime for a single socket to compute the fuel load it has to do. So, and here on this typical performance figure, you have two kinds of curves. One curve for the vectorized algorithms. This is what I call a vector here. And another one for the scalar algorithms. So every time when I will show you some performance metrics, some performance figures, I will always show you this kind of figure where you have here the number of macroparticles per cell, here the time, and the two kinds of implementation, the vectorized one, the plane, which is the plane line, and the scalar one. And this behavior is very typical. The vectorized algorithm is only efficient, I would say more efficient than the scalar one, when you are above a certain threshold, usually around 8 or 12 particles per cell. This is logical because vectorized algorithms need a lot of particles to be efficient. However, when you have few particles per cell, here the scalar implementation is still more efficient. This is the reason why we kept the two versions, and this is the reason why I will study the performance of the two versions in the next part of my talk. Then I would like to talk about the methodology. Here, for performance evaluation, I will use one single case, which is homogeneous thermalized hydrogen plasma in 3D with periodic conditions and second order interpolation. Why I'll use this benchmark? It's because here the load per computing units will remain approximately constant in time and space, creating a controlled environment where we need to keep the number of PC constant per cell. It runs quite quickly. I mean, I don't have to wait a lot of time before having a converged system. So I can run it just on few iterations, which is very nice to get performance results quickly. And it's sufficiently simple to be run on by similar peak codes in the world. So I know that my results can be reproduced or compared by my peers easily. However, it's a very academic situations without, I would say, with very few physical interest. About the performance comparison, I will use different systems. First, I will use, I would say, the classical processors that we use, that our users consider usually. So the Skylake processor, the Cascade Lake one, and the AMD Rome EPIC. And then I will take the A64FX and use three different compilers, the Fujitsu, the ARM, and the GNU one. The A64FX is provided not by the Fugaku. I mean, recently I've been using the Fugaku, but all the results here will be from metrics obtained on a small cluster we have here in France at TGCC. Here it's about the compilation flags, so I don't want to spend time on it, but the slide is here in case you have questions. And about the numerical parameters, you have to understand that the nodes will be fully loaded, and we have a constant load per core. It means that the total load per socket will vary depending on the processor that we use. But each core, whatever the system, whatever the processor, will have the same load. This is what you can see here. The load will be different according to the processor we will use, but it's always proportional to the number of cores. So before going to the optimizations themselves, let's just have a look to the performance without touching the code in the initial state before optimizing for ARM. So here again, you have the socket time per macroparticle per iteration here in the y-axis. And in the abscissa, still the number of macroparticles per cell. The main information here is that first, if you look at the A64FX, which is the green line for the GNU compiler, the red line for the ARM one, and the purple one for the Fujitsu one, the Fujitsu compiler is the slowest of all. Then you can see that the ARM and GNU compiler are performing a bit better without optimization. But in any case, here we are quite far from the, I would say, our reference, which is the Skylake processor. The Skylake processor is the blue line here. So of course, on such a figure, the lower is the better. So now what I will present is the different small optimizations that we have done in order to fill the gap between the Skylake and the different A64FX implementation and compilers. The first issue we have, so I need also to say that so far we mainly focused on the vectorization issues. And all the things we have solved and are presented here are things we obtained from the optimization reports mainly. So first, the vectorizations we had on the Fujitsu compiler was the fact that we had a lot of if conditions inside SIMD loops, such as this example. It's very basic. Usually, the Intel compiler can compile this kind of issue of loop quite easily. But here, it was preventing the Fujitsu compiler to vectorize. So basically, a simple solution is to externalize the if conditions. And here, if you have a very long loop, you can even do a kind of blocking, use blocking techniques to diminish the size of the buffers, for instance, while externalizing the if conditions. Another issue that we had was the non-automatic loop unrolling, particularly in SIMD loops. So this is a typical example here. You have the vectorizable loop first here, and inside you will have another loop, an inner loop, where the loop count is completely independent from the SIMD loop. So basically, it can be unrolled. But here, the Fujitsu compiler was not able to do it automatically. So what we have done is using a specific pragmas. Actually, this problem was not only on the Fujitsu compilers, it was also on the ARM and GNU one. So this is the reason why we are using a collection of pragmas coming from the different compilers in order to solve the unrolling issue. Another problem was the inlining. Even with the inline keyword, it was not sufficient. So we had to have the always inline attribute, such as this example, or in the ARM with the ARM compiler or LLVM, sorry, Clang or LLVM compiler, we could use as well this compilation flag in order to tell the compiler to inline even very long functions. Also, we had some issues with oriented object programming, and particularly calling class members in SIMD loops. This is this example here, where our contiguous arrays are members of specific classes. So a solution we found so far was to declare intermediate pointers pointing toward the internal arrays, the contiguous arrays, and use the pointers in the loops. We also had a kind of similar issue using the stdvector library. So Smilei is strongly dependent on this for the moment. And basically, all the inline members of the function that should be inline and are members of the stdvector are not well inline, or at least the vectorization is not allowed. So similarly, we had to declare some pointers pointing toward the raw data of each vector. Also about class members, so it was a bit more surprising, but we also had issues with the loop count here. Here the loop count is a function, a number function. So what you can do here, it's very simple. I just declare an integer before the main loop and use this integer here. But okay, the issue does not always come from the content, but also come from the loop count. Also, we had issues with multidimensional arrays. What I call multidimensional is pointers, multidimensional pointers. So this kind of declaration, where basically you will access the data in this way. So here again, in some cases, it was not vectorizable. So you have different possibilities. Here you can come back to 1D arrays. So just double star. However, in some cases, you may need to modify a lot of functions and structures in the code. In Smilei, we used instead small temporary contiguous buffers, storing only the data that were used inside the SIMD loop. So it means duplicating the data, but if you use small buffers, you also reduce the stride when you access the data. And it can be interesting as well from a cache blocking point of view. So it depends on the situation, but sometimes buffering the data can have additional effects. And this is one of the last issues. So we also have very long and complex loops. So sometimes the Intel compiler can vectorize easily very long loops. And of course, it was an issue for the Fujitsu one. So this is something quite well known actually, but splitting the big loops into smaller ones, particularly when you don't need to buffer the data, can be a good thing to get some better performance on the A64FX. So now let's look at the updated results. First, we come back to this figure. So the socket time per macroparticle per iteration here on the y-axis, and still the number of macroparticles per cell on the x-axis. So if you remember the previous picture, the previous figure without the code optimization, so all the compilers were performing less. So here, thanks to the different adaptation, we managed to fill the gap. And the strongest, I would say, the tiny difference, the smallest difference is for the ARM compiler. As you can see here, the ARM compiler is now very close to the Skylake results. However, for the Fujitsu one, we still have a difference. And the job now, what we are currently doing is trying to understand why we still have this gap. And for the GNU compiler, we can see that we managed to reduce the gap, but the difference is still more important than with the ARM compiler. Another way to look at the same information is to look at the speedup. So here it's the ratio between the time before optimization and the time after optimization. What is interesting is that the maximum speedup is obtained using the Fujitsu compiler, because at the initial state, the gap was really huge. But the difference between the initial and updated state is important. And that the GNU compiler is the one that benefits the less from the different adaptation. Another way to look at the same information is to look at the comparison with the Skylake directly. So here it's the ratio of the time on the Skylake over the time on the A64FX after adaptation. So clearly here the ARM compiler is the closest. And then you have the GNU and the Fujitsu. Fujitsu is twice slower. And here we have a factor of 0.9 with the ARM compiler. And so here I was mainly focusing on the vectorized algorithms, but we also have the scalar one. And we can see that for the scalar one, the situation is a bit different. The three compilers are performing very similarly. The ARM is a bit better, but the difference is much less important than with the vectorized algorithm. So I will skip this slide for time reason. I just want to focus on this last slide. So we compute the number of macroparticles computed per joule using the TDP of each processor. So it's a bit theoretical, but I think it's always interesting to look at the energy, I would say the energy efficiency, the energy picture, and not always only on the performance. So here, the Rome processor is still the most efficient because it's the more efficient also in terms of computational time. However, we can see that the A64FX processor is a bit better than the Skylake one, thanks to the TDP, the low TDP that it has. So this picture demonstrates that if we continue to optimize, the A64FX will clearly have a huge interest in terms of energy point of view compared to the current processor that we use for our simulations. So I would like to conclude now. First, we have made many different, I would say, small, simple optimizations. I would like to insist on that. We didn't do complicated things. These things are usually automatically achieved by the Intel compiler, but we can see that it's good sometimes to keep the knowledge about what's behind the optimizations when we are on new systems, new architecture. Just to summarize, if you have a code like mine, maybe you should pay attention to loop unrolling, inlining, data structures. So check the compiler optimization reports. This is a huge mine of information. So again, I've done very simple modifications. So it's simple, but unfortunately it's tiring and repetitive because there are many loops would say infected by the different issues. A64FX at the level of the Skylake and Cascade Lake processor after code modification using the ARM compiler. So far, the Fujitsu compiler is still behind, but we already have better results that I'm working on now. About the future work, so we like to do better analysis using the profiling tools. We also have to extend all of these modifications to the different physical modules. We are now testing the code on the Fugaku, so using, I would say, more powerful A64FX processor. And we also have a collaboration with ARM to test the code on the Gravity processor. So I would like to thank you all for your attention. I would like to thank you, the organization, and as well all our partners and the different institutions that give us access to different computing resources. Thank you very much.
So thank you, Mathieu. Is anyone have the question? So I have no.
There is a hand raised by.
Okay. So in Shu, yes, please speak up.
Hello, my name is Ruxing Shu. So I want to ask that just you said a lot of things for the Fujitsu compiler, but according to my knowledge, Fujitsu compiler has two kind of say backends. One is their own backends, but another one is cloud-based. So what one? Just which one are you just from which one are you showing the results?
Yes, very good question. So the results on the TGCC FX700 was with the Fujitsu backend. So what we usually call the TRAD mode. And now on the Fugaku supercomputer, I'm using the Clang mode mostly. And I've done an extensive comparison between the two. But because I'm still working on the results, I prefer to not tell you now what's the best. I have already some difference between the two.
Yeah, just
but,
just perhaps.
I'm still working on it, so I don't want to be.
Okay. Okay, thank you very much. Because just perhaps one thing I can say that just the two backends usually differ quite a bit on performance yielded.
Yes.
So and Fujitsu's compiler, in fact, it is it's updating quite frequently in the beginning of this year. So I'm not sure if you are using the latest version. Just two things to mention. Thank you very much.
Thank you. Yeah, actually, this is also the reason why I'm now using mostly the Fugaku supercomputer.
I see.
Because yes, I think for the updates of the compilers, maybe it's more up to date. I'm not sure, but yeah, this is also the reason why I'm using Fugaku, to be sure to have the latest documentation.
We got one question on the chat window. So Mathieu, good job. Did you have the time to access also for the impact of the HBM on A64FX processor?
Yeah, this is a good question actually, because so far I know that my simulation fit into the HBM. Also, the steps that were presented here on the Skylake processor, they are supposed to be slightly memory bound. Usually, the arithmetic intensity of these two steps here and here are around 0.1. So basically, I should benefit from the high bandwidth from this HBM memory. However, when I look at the profilers, it seems that the two steps here are mostly L1 issues. So certainly that certainly that the HBM is helping me, and the memory issues are more at the cache level.
Okay, so I have just very small the comment. So that you did a lot of the optimization and code modification, but we found that the two things you can do. The one is the software pipelining, and
Yes.
another is that prefetching. So talk later. Thank you.
Thank you.